Hello and welcome to the second of the lectures in this week 8 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the previous lecture, we have seen that fuzzy rules can be viewed as pairs of fuzzy points, and under this context, we could look at the approximation offered by a fuzzy inference system. A measure of correctness of it could be thought of in terms of its interpolativity property. We have seen, at least in the case of FRIs, that they are not automatically interpolative. In this lecture, we will begin our quest towards exploring when FRIs can be interpolative. In this quest, we will start with the simplest of them all, a single SISO rule. That is, we consider that the fuzzy rule base has only one rule and it's a single input, single output rule. We will see the conditions required on the underlying fuzzy logic connectives to ensure that this inference is interpolative. Note that we are looking at a fuzzy inference system as an interpolation of its rules, because we know that a fuzzy inference system, it approximates any given function by overlapping patches of its rules. So you can look at FIS itself as a function from f of x to f of y. We are looking at rules of the form AI implies BI as in fact pairs of data points, pairs of fuzzy sets AI BI, such that BI is actually the output obtained from the fuzzy inference system psi tilde when AI is given as the input. Rules are considered as the ground truth for us in the inference system. We're only looking at them as pairs of fuzzy sets. Clearly, one can construct many such fuzzy inference systems, many such functions from f of x to f of y. The question now then is, what is the basic measure of verification? Whether this really approximates the system function that we are trying to approximate. We have seen that one good measure is that of interpolativity. So pick among all these families, all these functions psi j tilde, that psi j tilde or those psi j tildes at which they are interpolative. That means at AI they actually give BI. Well, we have made some observations. In the case of single SISO rule, if you are using the CRI inference, the composition rule of inference mechanism, we have seen that some pairs of operations do make it interpolative, at least for the fuzzy sets that we have considered. For instance, if the T-norm that is used in the composition is the minimum T-norm, and if you use the Gödel implication to obtain the relation between the antecedents and consequence, in this case a single rule, that means capturing the rule into a relation using a Gödel implication, we saw that for this pair of operations, it is interpolative for the fuzzy sets A and B that we have considered. Similarly, if we consider both of them to be the T-norm, minimum T-norm, then it is interpolative. Or if we consider min T-norm for the composition, the product T-norm for capturing the relation in the rule, we saw that it is again interpolative. In the case of BKS, we have seen that if I were interpreted as clean Deans and F were interpreted as the Gödel implication, it is interpolative, at least for the fuzzy sets A and B that we considered. However, for another pair of combinations where we fixed the implication to be the clean Deans but varied the function f, which gives us the relation between the rule, between the antecedent and the consequent, if we vary them as minimum T-norm or the product T-norm, even for the fuzzy sets A and B that we have considered to form the antecedent and consequent in the single SISO rule that we have considered, it is not interpolative. This is what we would like to investigate in this lecture. Note that in the case of an FRI with a single SISO rule, we have just this rule that if x is A then y is B. We use an operation f to obtain the relation R from x cross y to 0, 1 as f of ax comma by, and the output of for a given input a dash is obtained by composing it with this R. So you could use the CRA, the compositional rule of inference, where we use the sub-T composition. This is how it looks like, the final formula. Or we could also use the BKS inference, which is essentially using the BKS product, the Bangalore cohorts of product composition, where I is an implication, and this is how it looks like. Well, let's look at a single SISO rule and a singleton input now. So let's assume that A implies B is what we are given, and A dash is in fact a singleton input. That means what we have is A dash is fuzzified at some point x0 element of x. That means if you look at it, this is your x, this is your x0, it is 0 everywhere else except at this point where it is 1. So this is the fuzzy set that we are considering. Now let's look at what happens at this point if we give. So we are looking at the CRA, B dash is A dash, so T R. So B dash is a fuzzy set on Y. So at a particular point it will look like this: supremum x element of x, T of A dash of x, comma R of x. Now what we can do is, we can write it like this: the supremum x not equal to 0, T of A dash of x, comma R of x, comma Y, join max with when x is equal to x0. So when x is equal to x0, is A dash of x0, comma R of x0, comma Y. Note that A dash is singleton fuzzified. That means outside of x0, when x is not equal to x0, this is in fact 0. And for a T-norm, when one of the arguments is 0, the entire thing becomes 0. So this is 0 joined with T of when A dash at x0 is in fact 1, comma R of x0, comma Y. Clearly this is equal to, because 1 is the left neutral element, or both left and right neutral elements for the T-norm T, what we obtain is R of x0, comma Y, which is nothing but f of A of x0, comma. So you see that B dash of Y is nothing but the membership value that x0 takes in A suitably modified on the corresponding membership value that Y takes in B. That is your B dash of Y. So if you're looking at this CRI, B dash of Y is A dash composed with R at Y, which is R of x0 Y, which is equal to f of A x0, comma B of Y. This is in the case of CRI. What happens in the case of BKS? Let's check that out. So in the case of BKS, B dash of Y is given as infimum x element of x, I of A dash of x, comma R of xy. Once again, we can split it like this: infimum x not equal to x0, I of A dash of x, comma R of xy, meet with I of A dash at x0, comma R of x0, comma Y. Now note that once again at this point, when x is not equal to x0, A dash of x0 is 0. R of xy definitely can have some non-zero values, but what we do know is I is an implication. I of 0 comma x is 1, which means this entire thing becomes 1 for every x not equal to x0, and what we are left with is this I of A dash of x0, which is essentially at this point it is 1 comma R of x0, comma Y, which is essentially I of 1 comma R of x0, comma Y. Now if I has the neutrality property, that means 1 is the left neutral element of I, then essentially this also becomes R of x0, comma Y, which is f of A at x0, comma B of Y. So in the case of BKS, again, if the considered I in the composition if it has the neutrality property, then b dash of y is nothing but f of a x naught comma b of y. Essentially, it means the membership value of x naught in A, the antecedent of the rule, is used as the similarity value to modify the consequent B. So you see here, the moment we have a singleton input, we are essentially making FRI look like a similarity-based reasoning scheme. Okay. Now with this, we can have a pretty simple trivial result, that if the antecedent that you considered originally, if it were a singleton fuzzy set, so the antecedent is a singleton fuzzy set, and if 1 is a left neutral element of f, that is f of 1y is equal to y for all y, then what we obtain is this result in the case of CRI, that is A composed with R is equal to B, which means we do obtain interpolativity. How do we obtain this? Let's look at this. We are looking at v dash of y. Once again, it is supremum x, element of x, t of. Now a dash is a of x, comma r of xy. Once again, we split this as x not equal to x naught. Remember, a dash is a singleton fuzzy set. Without loss of generality, we can take it to be the point x naught at which it attains normality 1, and rest all places it is taking the 0 membership value, t of a of x and r of xy. So t of a at x naught and r of x naught. Once again, at this point it is 0 for every such x equal to x naught. So this entire thing becomes 0. Join with t of 1 comma r of x naught comma 1. We have seen that this is nothing but, since 1 is the neutral element of t, it's nothing but f of a x naught comma y. At a x naught is 1, so we have f of 1 comma y comma b of 1. So if f has the neutrality property, that if 1 is the left neutral element of f, then we actually obtain close to b of 1. Similarly, we can show, just following the same procedure, step by step, we see that if I, the implication used in the BKS inference, does have the neutrality property, that means 1 is the left neutral element, then we see when the antecedent A is a singleton fuzzy set, then we do have interpolativity. Means if we give A dash as A, the singleton fuzzy set which is the antecedent, then we obtain the B. B could be any fuzzy set, not necessarily singleton. Okay, so this is the case with singleton fuzzy set. Let us consider the case where we have a non-singleton input. Towards helping us in this, let's look at a simple example. Let's fix a y naught element of y, and we are still in the single SISO rule case. Let's look at the membership value of y naught in B, the consequent of the rule that we are considering. Let's assume this to be beta. Now, so b dash of y naught is in fact given as follows. So we fix y naught, it is supremum over x, the running variable is x, it doesn't have anything to do with y, so we can fix this y to be y naught. Let's for the moment also assume that x has only 2 elements, and the antecedent A takes these as the membership values there. And let's try to calculate what is b dash of y naught. So b dash of y naught is equal to supremum x element of x, t of a of x. So note that we are giving a dash, but now we are checking for the interpolativity. So a dash is a, f of e of x, comma b of y naught. Now, since x has only 2 elements, x1, x2, we could write this as T of A of x1 comma f of A of x1 comma b of y0 supremum T of A of x2 comma f of A of x2 comma b of y0. Now, if you look at this, look at this second component. This is nothing but T of A of x2 is 1. So it is T of 1 comma f of 1 comma b of y0 is beta. This is what you obtain. Now, if you assume, so 1 is a neutral element of T. If assume that f also has 1 as its neutral element, this essentially turns out to be beta. Now, what is this value now? So what we have here is nothing but T of A of x1 is 0.3 comma f of 0.3 comma beta. So on the whole, what we have is T of 0.3 comma f of 0.3 comma beta or beta, maximum with beta. If you want this to be beta, you can ask the question, when will this be equal to beta? Because we want this b dash of y to be b of y0. Remember, this is essentially b dash of y0. So this is b dash of y0. We want this to be equal to b of y0. So when will this be equal to beta? Well, clearly we want that this value here should be smaller than beta. That means we want that T of 0.3 comma f 0.3 comma beta is less than or equal to beta. If it is less than or equal to beta, then the supremum of these two, which is max in this case, is actually beta, and we will obtain this. If this value were to be greater than beta, then it will no more be beta, the maximum will be this first component, which will be greater than beta, and we will not obtain interpolativity. Taking cue from this, let's do some algebraic calculations and maybe perhaps a little manipulation. So what we have is b dash of y is equal to supremum x element of x T of A of x comma r of x. Now, let us assume for a moment that A in fact is normal. So we are considering the CRA composition with a single rule AB. F is the operation used to relate the antecedent A to the consequent B to obtain the relation R, and we are considering the CRA inference, which means it's T composition. Let's for the moment assume A is also normal. So that means we could write it like this: supremum x element of kernel of A T of A of x comma r of xy. Note that kernel of A means the value 6 in the support of A, where the membership value is 1 in A, means where A attains normality. This joined with supremum x not in the kernel of A T of A of x comma r of xy. Now, let us fix y0. Once again, let us fix b of y0 to be beta. So now what we have here is equal to, look at this, when x belongs to the kernel of A, then this value is 1. So what we will have is supremum over x element of kernel of A T of 1 comma r of x comma y max with supremum x not in kernel of A T of A of x comma r of xy. Now, writing it in terms of the corresponding f, what we obtain is supremum over x element of kernel of A T of 1 comma f of r of x comma y is f of ax comma by naught. We are fixing the y naught. Supremum x not in terms of u. T of a of x comma f of a of x comma b of y naught. Now, let's assume on this point a of f of x here, since we are taking x from kernel of a, we know that f of ax is 1, which means rewriting this, what we obtain is the first component turns out to be, for every x there, the supremum can be removed now because it does not affect b of y naught. If 1 turns out to be the neutral element of f, so let's add this assumption that 1 is the left neutral element of f, then we obtain this to be b of y naught or supremum x not in kernel of a t of, for the moment let us assume that for each of these x it is in fact some alpha x, f of alpha x comma beta. So we have assumed that beta of y naught is beta, b of y naught is beta. This is the equation that we get. Now what we want is, we know that this is beta b dash of y naught. We want this to be equal to in fact beta, which means this entire quantity should be less than or equal to beta. And for every alpha x, remember x is varying over the non-kernel part of a, that means alpha x, which is nothing but a of x, is actually a value less than 1, but it could be any value less than 1. So now we want that this entire supremum is less than or equal to beta. Remember, this beta is fixed quantity. So in essence, what we want is for any alpha, t alpha, f alpha, beta should be less than or equal to beta for all alpha and 0, 1, perhaps including 1, it's fine. And note that once again, this beta is an element that we have arbitrarily fixed. B dash of y naught is arbitrarily fixed as some value beta, which means this should happen not only for alpha but also for beta. So this is the inequality that we want t and f to satisfy. So if we add this also as the condition, let the pair t comma f satisfy the following functional equality: t of alpha or comma f of alpha beta is less than or equal to beta for all alpha beta coming from the 0, 1 interval. If we have these three conditions, we see that in fact b dash of y naught is equal to b, which is b of y naught. Note that y naught was originally an arbitrary point that we took, which means b is in fact equal to, b dash is in fact equal to b. So now this is the condition that we need on the underlying operations t and f for CRI to be interpolative, given that the antecedent A is normal fuzzy set and f has 1 as the left neutral element. Let's quickly check the observations we have made earlier, the examples we had. We saw that if you take the minimum t norm for the t and the Gödel implication for f, it turned out to be interpolative. In fact, it can be shown that it does satisfy this functional inequality. Well, let's verify this. So the functional inequality that we are considering is this: p of alpha comma f of alpha beta should be less than or equal to beta for all alpha element of 0, 1. Now let's consider t to be min and f to be the Gödel implication. This is nothing but 1 if x is less than or equal to y and y if x is greater than y. So now consider this right here. So substituting minimum for t, minimum of alpha, I Gödel alpha comma beta. Now we can write it like this: equal to minimum of alpha comma. Note that if alpha is less than or equal to beta, it is 1, and if alpha is greater than beta, it is alpha. It is beta. So now this is essentially, if alpha is less than or equal to beta, it is minimum of 1 comma alpha if alpha is less than or equal to beta, and it is minimum of alpha comma beta if alpha is greater than beta. Clearly, if alpha is less than or equal to beta, it is alpha, and if alpha is greater than beta, then minimum of alpha beta is beta, and we see that this entire thing is always less than or equal to beta. So the pair Tm comma Gödel implication, this pair T comma F does satisfy this equation in functional inequality TFC, and hence we also see that it is interpolative. It can be easily verified that if we consider the min T-norm for both T and F, once again it does satisfy TFC, essentially the property of a T-norm. What we want is min of alpha comma min of alpha comma beta. We know that min of alpha comma beta is always less than or equal to beta, and this is less than or equal to beta. In fact, any T1, T2 we consider by the properties of T1, we know that T2 of alpha beta is less than or equal to beta, so it is T1 of alpha beta less than or equal to beta. So we see that even for the other pair, where we consider min for the T-norm and product for the function f, which gives us the relation in the rule, we see that they do satisfy this inequality. If we consider this pair, Tm and the Klein-Dien's implication for the f, we have not seen an example, but we can ask the question, is it interpolative? Let's verify whether it satisfies is the equation TFC. Note that we have here T is Tm, F is IKB, and we are looking at this inequality for every alpha beta. So this translates into minimum of alpha comma IKB is maximum of 1 minus alpha comma beta. The question is it always less than or equal to beta? This is the question that we are asking. But easily it can be shown that if, let's assume that the alpha given to us is such that 1 minus alpha is less than or equal to alpha, and we pick a beta from here. For this pair of beta comma alpha, you see here, max of 1 minus alpha comma beta is in fact 1 minus alpha. Then this implies min of alpha comma 1 minus max of 1 minus alpha comma beta is in fact equal to min of alpha comma 1 minus alpha. It could, from this we see that it is in fact 1 minus alpha, which is greater than beta and not less than or equal to beta. Of course, if you take alpha to be say 0.8, then 1 minus alpha is 0.2. If you pick beta to be 0.1, this couple alpha and beta satisfy this inequality, this triple of inequalities, and we see that for that pair alpha beta, Tm and IKD do not satisfy this inequality. Thus, they are not interpolative. If we consider the BK as a product, we can pretty much get the same result, except that we need another condition on I. If you consider the antecedent A to be a normal fuzzy set and 1 as the left neutral element of F, and I satisfies NP, that means 1 is also the left neutral element of I. Note that in the case of a T-norm, this was already given because 1 is a neutral element of T-norm. It can be shown that a dual kind of an inequality, functional inequality, plays a role in obtaining interpolativity. What is that equation? This equation, I of alpha comma f of alpha beta should be greater than or equal to b beta for every alpha beta in 0. If this condition is satisfied, then we obtain that the B case inference with this I, where the antecedent A is normal fuzzy set and F has 1 as its neutral element, left neutral element, we see that it is also interpolative. Let's revisit the examples that we had. In the case of B case, we have seen that if we consider Klein-Deans for I and Gödel for F, we obtained that for the considered A and B it was interpolative. We will show it does in fact satisfy this inequality I of C. It's quite easy to see. So what we have is, we need to show IKD of alpha and I Gödel of alpha comma beta is in fact greater than or equal to beta for every alpha beta element of 0. Now that is the equation, that inequality that we have here, greater than or equal to beta. What is this? The left hand side is maximum of 1 minus x, Gödel is 1 if alpha is less than or equal to beta, beta if alpha greater than beta. And this will turn out to be maximum of 1 minus x, 1 minus alpha, 1 if alpha is less than or equal to beta, and if alpha is greater than beta, then what we get is maximum of 1 minus alpha, and what we have here is maximum of 1 minus alpha, 1 is always 1, and alpha is less than or equal to beta. If alpha is greater than beta, what we get is maximum of 1 minus alpha, beta. Now note that when alpha is greater than beta, it is max of 1 minus alpha, beta. So if it is beta, it is definitely greater than or equal to beta. If it is maximum is 1 minus alpha, which is clearly greater than beta, then it is greater than or equal to beta. So we see that for this pair of implications taken to be as I and F, in the case of B case inference, we do obtain interpolativity, and that's because the IFC functional inequality is satisfied. In the other cases where we have the Klein-Deans implication for I and minimum for the F, we saw that it was not interpolative, at least for the fuzzy sets A and B that we considered, but that's because it does not satisfy IFC. Once again, this can be easily shown. So we need to see whether IKD of alpha and Tn of alpha beta is greater than or equal to beta for all alpha beta element of 0. This is nothing but max of 1 minus alpha, min of alpha, beta. We are asking the question, is it actually greater than or equal to beta? Well, clearly, if we take beta to be 1, what we get here is max of 1 minus alpha, alpha. That's what we get here. We are asking the question, is it greater than or equal to 1? Well, definitely not when alpha is greater than 0. In fact, it can be shown that if we have an implication and a T-NOC, this inequality, for it to be satisfied, if it is satisfied, this means I in fact has the identity principle. How do we know this? Let's assume that this inequality is satisfied, and let's take beta is equal to 1. And what we have is I of alpha, T of alpha beta. Now beta is 1, which means it is I of alpha, alpha. It has to be greater than or equal to 1, which means it is 1. So I of alpha, alpha is 1 for all alpha and 0. So you see here, the Klein-Deans implication does not have the identity principle. So with this implication, if you take F to be a T-NOC, it is not going to satisfy IFC, and hence it will also not satisfy interpolativity. Now, why did we tag this inequality as IFC and the previous one as TFC? Because there is a functional inequality involving the T-NOC T, a T-NOC T and an implication I as follows. You will see that if you put F here, this is essentially TFC. This inequality has been studied in the literature under the name of T-conditionality. That is why we came up with this tag, in the sense abbreviating TF conditionality and IF conditionality. Now, it has been quite well studied for which pairs of T and I, T-norms and implication I, this inequality is valid. One family of implications for which this is valid is essentially the R implication. Recall that if you are given a T norm, the corresponding R implication is given as follows. IT of xi is supremum over T such that T of xt is less than or equal to y. We have seen its origins, how it comes from writing A complement union B in an alternative equivalent form in set theoretic terms. Now the result, an easy result can be proven, which says that if this T norm is originally left continuous, then the pair T, IT, the corresponding residual, this pair indeed satisfies this T-conditionality. But how do we prove this? The proof is not very difficult. Please recall, we introduced the algebraic structure called the residuated lattice. What's a residuated lattice? It is this following structure. It has a set L, non-empty set L, with these two lattice operations, join and meet, and two further binary operations, star and this arrow, along with these two constants 0 and 1, which are elements of L, such that L join meet 0 1 is a bounded lattice. So 1 is the upper bound and 0 is the lower bound, and these are the join and meet of the lattice. L star 1 is an ordered commutative monoid with identity 1. So that means this operation star is compatible with the lattice order imposed on L. It is commutative. It's a monoid. That means associative and neutral element exists. In fact, the neutral element is 1, and we know that the neutral element 1 is also the largest element with respect to the order given by the lattice. So it's an ordered commutative monoid with identity 1. And importantly, these two operations, star and arrow, they form an adjoint pair on L. What does it mean? That means they satisfy this particular equivalence condition. Whenever P star Q is less than R, then P arrow R is greater than or equal to Q. Now, we have seen that if we take L to be 0, 1 and star to be a T norm and implication to be the corresponding R implication, we can obtain a residuated lattice. It was clear to us earlier too that if you consider the T norm T1 0, 1, then in fact this structure is an ordered commutative integral monoid. It is only a question of obtaining a corresponding arrow operation which will satisfy this adjointness property, and we have seen that if T is left continuous, this structure in fact where this arrow is given by the residual of the corresponding T norm is in fact a residual lattice. So now we are interested in this particular functional inequality, which is the T-conditionality, and we are looking at the implication to be an R implication. We know that this property, the restitution property, is satisfied by the pair T and IT. It is in fact clearly and easily from this residuated property we obtain this result that whenever T is left continuous, T of IT satisfies TC. Now the proof is immediate. Perhaps it's good to see that. Note that we are looking at T and IT. We know that the restitution property is satisfied. That means if T of xy is less than or equal to z, if and only if IT of xz is greater than or equal to y. And what we need to prove is the T conditionality. That means T of x comma T of IT of x comma y should be less than or equal to y. So this is the property that we want to prove. So let's assume that for some xy, we know that, let's put it like this, IT of xy is in fact equal to IT of xy. This is clear. We can also rewrite this as greater than or equal to. So now look at this as xy and this as the z, which immediately implies T of x comma IT of xy is less than or equal to z. Okay, perhaps an easier way to see this is like this. If we could write in terms of alpha beta, so T of alpha beta is less than or equal to gamma if and only if IT of alpha comma gamma is greater than or equal to beta. And what we need to prove is this quantity. So now let's take IT of xy. We know this is trivially greater than or equal to IT of xy. Now we assume x to be alpha, y to be beta, and IT of xy to be y to be gamma and it of xy to be beta, and this implies t of alpha is x, comma, beta, which is it of xy, is less than or equal to gamma, which is 1. And this is the T-conditionality that we wanted. So clearly, for this family of implications, R implications obtained from left continuous T-norm, we see that the corresponding T and the residual do satisfy T-conditionality. Well, so if you use a left continuous T-norm for in the composition of CRI and use the residual implication for F, that is to obtain the relation from the rule A implies B, then we see that CRI is in fact interpolative when the antecedent A is normal, because F already has the neutrality property, and T conditionality will be satisfied by the pair T comma IT. Well, look at this. We have discussed only the case of single SISO rule. We need to discuss the case of multiple rules, but a quick recap of what we have seen in the previous lecture. You see here, when we consider the CRI for a single SISO rule, this pair, minimum and Gödel implication, they satisfy TFC and hence they give rise to interpolativity. However, in the case of multiple rules, when you consider the same pair for T and F, and even in the case of different aggregation operators G and different inference strategies theta or phi T, they are not actually interpolative, which means we need to discuss a little deeper in the case of multiple SISO rules. In this lecture, we have looked at interpolativity of FRI with a single SISO rule. What is very interesting is the important role played by functional inequality involving the underlying operations. And also, happily, one of the algebraic structures that we have discussed earlier, that of residuated lattices, has surfaced here. But this allows us to only discuss interpolativity in the case of single SISO rule. What we want to discuss is the interpolativity in the case of multiple SISO rules. And this is what we will take up in the next lecture, which will lead us to discussing fuzzy relational equations in depth. Glad that you could join us today for this lecture and hope to see you soon in the next lecture. Thank you again.